So we've been discussing electrophilic addition reactions to carbon-carbon double bonds to kind of complete the picture of these elementary addition reactions. Now we need to turn our attention to a different functional group. And really this functional group is not a functional group per se, but rather a family of functional groups. We're talking about a carbon-oxygen double bond in the context of either an aldehyde or a ketone. These reactions will undergo nucleophilic, acyl meaning the carbon-oxygen double bond, addition reactions. The reason that it's called nucleophilic addition is that the group that is going to add to our double bond is going to be nucleophilic rather than electrophilic. So this pi bond is not going to be our nucleophile. Because there's a very large electronegativity difference between oxygen and carbon, the carbon is going to have a significant deficiency of electron density. As a result, it is going to be the best electrophile available in the reaction, and it will undergo nucleophilic attack. Now, one of the interesting aspects of this is that the hybridization is sp2 hybridized. So I can have approach of the nucleophile from above the plane as it's rendered on this slide, or I could have attack from below the plane. Because of the hybridization of the electrophile, either of those two approaches are going to be facilitated. And also, because I have a very weak pi bond, I can have nucleophilic attack before I have the next step of the reaction. So again, the driving force for this is carbon can make no more than 4 bonds, and this will be facilitated in one single step. So this intermediate is obtained after one step, and then in the second step, we will have an acid-base reaction to convert the carbonyl oxygen to an alcohol. Let's look at some specific reactions and see how mechanism is involved in each of these processes. So as my model system, I'm going to use 2-butanone. One of the interesting aspects of nucleophilic acyl substitution is there are 2 different mechanisms that can occur, and it all depends upon the nature of the nucleophile. So I'm going to draw 2 molecules of 2-butanone, and we'll discuss both of these mechanisms. One is called acid-catalyzed, and it tends to be the more popular of the 2 because of the nature of these nucleophiles. When you have a weak nucleophile, like water, like cyanide ion, like ammonia, you need to kickstart this reaction by making the carbonyl carbon more electrophilic. And that is typically accomplished with a simple proton transfer reaction step Of course, we've talked about the proton transfers in fairly good detail in the previous week or two in class. So the carbonyl oxygen and one of its lone pairs acts as the best nucleophile. Of course, our acidic proton is our best electrophile, and we'll have heterolytic bond cleavage. Our conjugate base is expelled. And of course, this is an isolable intermediate. And what's really significant about this intermediate is you've got an oxygen atom, a very highly electronegative atom that is significantly electrophilic. And it's not going to take this lightly, if you allow me to personify oxygen as not taking something lightly. And it will really strip the carbonyl carbon of a more electron density. And so what I've really done is activate this carbonyl carbon as a very reactive electrophile. And so what I can now do is have nucleophilic attack. And of course my pi bond will break so that carbon, again, is not making more than 4 covalent bonds. And of course this will afford a carbon nucleophile bond and the corresponding alcohol. It's a two-step mechanism. The first step is proton transfer. The second step is nucleophilic attack. This is the sequence when I have a weak nucleophile. And we'll go through a couple of examples of this particular type of mechanism. Again, we could also have a strong nucleophile. And this is called the base-catalyzed mechanism. Now the name is a bit of a misnomer because there really isn't a base that's present. The base is the strong nucleophile. An example of a strong nucleophile would be hydride, hydrogen and its electrons, or a carbanion, or a hydroxide, or any base that is the conjugate of a fairly weak acid. So in the first step of the mechanism, you will have nucleophilic attack. Notice that this is going to afford a negatively charged intermediate, whereas in the acid-catalyzed mechanism, there was a positively charged intermediate. And as you might suspect, in the second step, there is a proton transfer. Also want you to notice that whether it's acid-catalyzed or base-catalyzed, the same chemistry is occurring. We're making a carbon nucleophile bond and we're making an oxygen-hydrogen bond. The steps are just reversed because in the base-catalyzed mechanism, we have nucleophilic attack first, and we have proton transfer second. In the acid-catalyzed reaction, we have the proton transfer first and the nucleophilic attack second. So what I'd like to do at this point is look at some real examples. I think there are about 3 or 4 different mechanisms I'd like to go through and ask you to master at this point. And the first of these is going to be the formation of a hydrate. Our nucleophile in this mechanism is the water molecule. This is a weak nucleophile. Therefore, we want an acid-catalyzed mechanism. We start with 2-butanone again. Our other reagent could be HCl. Remember, when you're pushing your arrows, every heteroatom must have all of its lone pairs present. So in the first step, we're going to have a proton transfer. And Cl minus is our leaving group. Our intermediate is a positively charged intermediate. And at this point, again, we have a competition for nucleophiles. First of all, we have the water molecule. The water molecule is a weak nucleophile. We also have in solution chloride ion, also a weak nucleophile. The principle is simple. The stronger nucleophile will attack this highly reactive carbon electrophile. And if you recall from previous reactions, water is the better nucleophile as compared to chloride, even though it's neutral and chloride is negatively charged. Water attacks. I get an alcohol. And a protonated alcohol. This is called a diol, and more specifically, it's called a geminal diol. We've talked about this nomenclature before. We'll call it gem diol for short. But we're not quite done. We need to alleviate the positive charge on this oxygen. Normally when we see an acid in an organic reaction, it is almost always catalytic, which means we need to regenerate our HCl, and we do at the very end. Now I have the expected gem diol. So this is the formation of a hydrate. And of course, at the very end, HCl is regenerated. So the HCl is catalytic, whereas the H2O is a bona fide reagent. Notice that the H from HCl is incorporated into the molecule. So in order to be completely accurate, let's color code. This hydrogen came from HCl, whereas the hydrogen in HCl that we get at the end comes from water. So if we were to radial label these hydrogens, they would be incorporated into different molecules. So even though we regenerate HCl, and even though technically the HCl is catalytic, you don't regenerate the same atoms that you had. Certainly you regenerate the same chlorine, but not the same hydrogen. So this is an example of a weak nucleophile undergoing a nucleophilic acyl addition reaction. Now let's take a look at one in which the nucleophile is strong and not weak. And this is chemistry that we will look at in more depth towards the end of the semester. This reaction is technically an oxidation reduction reaction. And I want to use the same substrate that I've been using. Butanone. And now our reagent is lithium aluminum hydride. Normally aluminum makes 3 bonds when it's neutral. Lithium aluminum hydride has a tetrahedral geometry and this aluminum has an integer minus charge. Of course, the lithium cation has an integer positive charge. And the way that this works is that you actually have a complex formed between the oxygen and the aluminum, and one of these hydrides leaves. So in all honesty, the true nucleophile in this reaction is hydride. Now this mechanism is complex. I'm going to simplify it for the time being, but at the end of the year I will give you the full mechanistic details of this reaction. So this one's pretty simple. Since I have a strong nucleophile, this is going to be base-catalyzed. So in the first step, nucleophilic attack. I get a negatively charged substrate. So this intermediate has an overall negative charge. And then of course, in the second step, I'll have a protic acid and we'll have a proton transfer that will yield our reduced product. Notice that we've gone from a ketone to an alcohol. In the organic world, an organic substrate has been reduced if you count the number of bonds that carbon makes to atoms more electronegative than itself. And that number gets smaller as you go from reactants to products. So in the initial reactant, carbon is making 2 bonds to an oxygen atom, which is more electronegative than carbon, but in products it's only making one bond. So we would say that carbon has been reduced. If carbon has been reduced, then another species must be oxidized. So as a question, what is the chemical species that has been oxidized in this reaction? That's something for you to consider. What species has been oxidized? So this is an example of base-catalyzed mechanism. One other reaction I want to show you, and then we'll call this a complete introduction to nucleophilic acetal substitution, and that is going to be the reaction of cyanide to a carbonyl. And again, to be consistent, I'm just going to use the same carbonyl. I'm going to use HCN. This is one of those reactions that's awesome to do on paper and horrible to do in lab, because HCN is the reason why cyanide is as toxic as it is. So cyanide is a weak nucleophile. I want to undergo the acid-catalyzed mechanism, so we want a proton transfer in the first step. Activating our carbonyl carbon as an electrophile. And then attack of cyanide. Now, you've got a lone pair of electrons on nitrogen. You've got a lone pair of electrons on carbon. But it's the carbon in which those electrons are more nucleophilic, because it's the less electronegative atom. Lone pairs are more reactive, less stable on a less electronegative atom than on a more electronegative atom. So we're going to make a carbon-carbon bond. Notice this is the first mechanism that I've shown you in which you can make a carbon-carbon bond. Pi bond's going to break. And we are going to make a molecule called a cyanohydrin. If you remember from electrophilic addition of alkenes, when we added a Br atom and an OH functional group across the double bond, we called that a bromohydrin. This is a cyanohydrin. All right, so that covers the mechanisms that I want to emphasize right now. I'm going to leave you with a challenge problem that's actually in your problem set. And I just want to go through the mechanism and emphasize how they all follow the 4 patterns of mechanistic thought that we've been discussing the last 2 weeks in class. And this is going to be a reaction of an alcohol in which there are 2 alcohols in the same molecule. We call this an acetal, and I will emphasize this a whole lot in the second semester course. So again, I want to start with 2-butanone. And I'm going to react this with ethylene glycol, or 1,2-dihydroxyethane, or ethane diol. Any of those three names would apply. This is a weak nucleophile, so of course I need a strong acid catalyst. So let's look at how this is the same in terms of what we've been discussing, and then what makes it a little bit more difficult. This is a 6-step mechanism. And the first step is going to be pretty simple. Proton transfer. We know that's going to occur. Second step, nucleophilic attack. That should be no surprise. Now, we need to alleviate the positive charge on this oxygen. The most likely candidate for that. So this is simply another proton transfer step. This is the conjugate base of our acid. At this point, the carbon that used to be a carbonyl is now an alcohol, but it is also an ether. Carbon, oxygen, carbon. Carbon, oxygen, hydrogen. This molecule is called a hemiacetal. This is what happens to glucose when it forms a ring. Glucose in the cyclic form is a 6-membered ring. In vivo, when it reacts in glycolysis, 99% of the glucose molecules are hemiacetals. However, this can react further. So I'm going to open a new easel. We'll start with what we had made, our hemiacetal. Now there are no other reagents. I think that's important to keep in mind. We do have our acid that remains in solution. And we can protonate the other oxygen. In other words, all we've done is transfer a proton from our nucleophilic atom that attacked and made a new bond. So from here to here, we've done a proton transfer. And we've accomplished this with the help of a proton transfer agent, our conjugate base of our acid and the parent acid. At the end of this, we now have a molecule that has an excellent leaving group. Because if this bond were to break, this positively charged oxygen would now be neutral. And the most likely way that this is going to occur is to increase entropy. So the attack comes from within the molecule, so you go from one molecule to two molecules. In other words, we expel water. Water is a leaving group. Okay, so this is loss of a leaving group. One of those four patterns that we've seen. This is a proton transfer. And if we go back, this was a proton transfer. This was nucleophilic attack. And of course, this is a proton transfer. So stringing this all together, proton transfer, nucleophilic attack, proton transfer, another proton transfer, loss of a leaving group. Nothing is outside the box of what we learned previously. It's just more complicated now. Our intermediate, you now have reformed a carbonyl-like molecule. This makes the carbonyl carbon, again, exceptionally electrophilic. And now the free OH can attack the pi bond breaks. This is nucleophilic attack. Now this carbon is engaged in two ether linkages. The only thing that's really left to do at this point is to neutralize this molecule. And when we have two ether linkages, this goes from being called a hemiacetal to now being called an acetal. This is what happens when two glucose molecules in their chair conformation link together to make a disaccharide. We get an acetal. Now the interesting thing about this mechanism is that it gives us a way of protecting a carbonyl from reacting, and we put it on under acidic conditions. It is stable under any other kind of reaction conditions except acidic conditions. And acidic conditions would promote the reverse reaction of what we've just demonstrated in the forward reaction. So let's recap what these steps are one more time. Step 1 is a proton transfer. Step 2 is nucleophilic attack. Step 3 is a proton transfer. Step 4 is a proton transfer. Step 5 is loss of a leaving group. Step 6 is nucleophilic attack. And step 7 is a proton transfer. Complicated because of the number of steps, but not the quality of the steps, because these are all consistent with patterns of mechanistic thought that we have been discussing for the last 2 weeks in class. So this wraps up nicely what I wanted to cover in terms of examples of addition reactions that use these 4 patterns of mechanistic thought. To review, we looked at 4 reactions of, let me just bring another slide as we review this. So the substrate I used in all of our examples in class was this asymmetrical substrate. We learned that HBr adding across this double bond would result in a rearranged product. We learned that the addition of water with acid would also result in a rearranged product. We learned that Br2 would result in a non-rearranged product with anti-addition. And we learned that Br2 with H2O would result in a non-rearranged product, but that the OH would always go to the more substituted carbon, and it would be an anti-addition as well. Now, in both of these 2 molecules, we will also produce what we call an enantiomer. This is what we're going to be discussing in class this week. And so we'll probably revisit these reactions both in the stereochemistry unit and also in the substitution unit, because we saw the last steps were SN2-like, which facilitate backside attack of the nucleophile. Also, in this particular podcast, we looked at another 4 reaction mechanisms, all of these of which are nucleophilic acyl addition. We added the elements of hydrogen and cyanide across a double bond to get a cyanohydrin. We reduced a carbonyl to an alcohol with lithium aluminum hydride in the first step, and then an aqueous acid in the second step. We produced a hydrate with the acid-catalyzed addition of hydrogen. Remember, this gives us a gem diol. And finally, we learned a little bit about protecting groups, where we added ethylene glycol with an acid catalyst to afford an acetal, which can come off of this reversibly. So if I were to add H3O+, I would get 2-butanone back again. So this serves as a nice introduction to addition reactions. This week in class, we will begin to master stereochemistry.